Hello, this is Britt Caswell with another video of examples for Algebra 2. This is covering Lesson 1-2, Example 2 in the SavvasRealize Algebra 2 textbook. In this video we are going to be covering reflecting functions across the x and y axis, which I really enjoy doing. So, this first example. It's starting with a graph, 2x minus 6, which I've already graphed for us. This is f of x. So what we're doing, if we are reflecting it across the x-axis, right, that one's the x one, is we take each point and however many up it went, for example, we would go down that many. So like here, the graph goes up by 4. I'm going to make it go down by 4. Here, the graph went down by 6. I'm going to make it go up by 6. And in as straight of a line as possible. Oh my good gravy. I'm going to connect those points. So here I've done my reflection. Okay. Notice that this is symmetrical. If I pretended like my x-axis was the belly of a butterfly, I'll even draw that in there for you. We'll delete this in a second. But if that x-axis was a belly of a butterfly, like this, then these two wings should theoretically match, right? I'm sure you guys have seen that example of symmetry. So that's how you know that you have done a reflection properly, is it'll be symmetric with respect to whatever axis you chose to use. That's going to be a big deal when we start reflecting across things that aren't just an axis. So then we have to go through and we have to create the equation of this new function. This is called the g function. So since it's linear, let's go ahead and let's just use y equals mx plus b, okay? Remember where m is the slope and b is horribly written there, but b is our y-intercept. So if I were just trying to write the equation of this line here, well, my slope, it's hard to kind of tell here, but it falls by 2 and it runs by 1, falls by 2, runs by 1. So my slope here is a negative 2x. And then my y-intercept is now at a positive 6 instead of a negative 6, so it's a plus 6 here. So notice that by reflecting across the x-axis, I have gone ahead and flipped both of the signs here. Now really what we're doing is we are doing this. Okay? We did a, well, I guess I should put it differently. We did a vertical transformation, right? A vertical flip, essentially. And so in doing that, what we were doing was we were taking f of x and we were plopping a negative in front of the set of parentheses. Recall in my last video, I told you guys, if you guys do some kind of transformation outside of the grouping symbol, it's going to have a vertical effect. That's why we did this. And then if you use the distributive property, that's what causes both of these signs to change. It's a little harder to see with a linear graph, to be honest with you. But kind of there it is. Another way that somebody might write this is they're saying f of x is equal to negative f of x, right, is equal to g of x. So you might also see that written out where they don't explicitly state the function, but they put like this general notation out here, which is a little weird. So this is like a generalized form. Here is for a specific function. So again, to flip it across the x-axis, which is a vertical reflection, put that word there to help us out. We ended up putting a negative outside of the grouping symbols. We distributed it, and that caused that flip. Let's check it out for part B. So part B gives us the same line, but now they want us to reflect it across the y-axis. So if I'm reflecting across the y-axis, I can take all the points that are generally, easy to see. For example, this point is 1 away, and I can move 1 to the left instead. Okay, so you could take all of the really friendly points and kind of scoot them this way and reflect it. Hopefully you draw a straight line. I'm trying my best here. Alrighty. So when I reflect across the y-axis, this turned into a horizontal reflection, didn't it? I could draw my little butterfly right here and my wings. So this was a horizontal reflection. People tend to get thrown off when they hear reflecting across the y-axis because they automatically associate that y with being vertical. But if you think about it, going across the y-axis is actually a horizontal change. So if there's a horizontal change, we're doing something within the grouping symbol, which you guys are going to see here in just a second. So just using what we know with slope-intercept form, let's look at this slope here. Okay, our graph falls by 2, runs by 1, so we have a slope of -2. And the y-intercept is still at -6. So the only change occurred right here in front of the x. Okay, so if I were to think about my grouping symbol here, it would have been right there. So if we do f of x, and you take a negative to wherever x is, you replace x with a negative, you're going to get your g of x, and that's going to be a horizontal reflection. So let's take a look at another one. So this one is a quadratic, right? We have our parabola. And let's talk about reflecting it across the x-axis. So if I'm doing it with just an equation, and I'm reflecting it across the x-axis, what I'm going to do is I'm going to take the entire equation, x squared minus 2, I'm going to plop a negative in front of it. Okay, so outside that grouping symbol gives me that vertical reflection that I want. And so what ends up happening is I can distribute this negative, and I get -x squared plus 2. In terms of translations, right, that plus 2 you learned was where you move the vertex up by 2. And a negative in front of the x squared, that's telling you that when I move 1 unit to the side, I move 1 unit down. 1, 2, 3. So here we go. Here is that reflection, which I would encourage you guys to check out on Desmos. Make sure that you do it right. So notice that I didn't actually use the graph to help me do this one. I just went ahead, plopped a negative in front of the whole thing, and went after it. So now let's try reflecting it across the y-axis. So if I go to reflect across the y-axis, I am taking the value where x is, and I'm replacing it with -x. But in this case, right, -x times -x goes back to being +x, doesn't it? So that would be a +x squared. And look at it. This is a symmetric drawing, right? This is something we call an even function, just so you guys think about it for later on. But we have this symmetric function, so it makes sense if I were to reflect it here horizontally, right? This moved about 1.5 this way. This one moved about 1.5 that way. That I'd get the exact same graph. And if you notice, by plugging in the negative x here, I still got the exact same equation. Kinda neat. So that is example number 2 with reflections. Until next time.